Hello, everyone. My name is Rachel Carter. Here we go. And I'm a project manager at Assisted Management Solutions. We are an environmental consulting company located in Southern Maryland. And my talk today is focused on some testing we did the last couple years at military installations for our Navy client. So the first thing I want to do is a little bit of background on non-residential buildings compared to their residential counterparts. So large non-residential buildings, such as those found on military installations, usually have large air handling systems that greatly affect pressure within the building and therefore radon levels. If the HVAC is working properly and has forced air, then that building is going to be under positive pressure, and that's going to deter radon gas from entering into the building. Alternatively, if that HVAC is not working properly, you can have negative pressure in the building, and that's going to draw radon gas into the building. The impact of HVAC in these buildings is usually greater than temperature and or other environmental factors such as wind or rain. And in many cases, these buildings can have one or two rooms that are elevated or a section of rooms, and this is most likely due to having an imbalanced HVAC unit. Additionally, these large air handling units, when operated as designed, can move a lot of air, causing a better played out of radon decay products, or RDPs, leading to lower equilibrium factors, EF, compared to smaller residential dwellings with less robust air handlers. There's also a few government and military concerns. Usually funding is the primary factor determining the mitigation timeline at these sites. So it could take years, unfortunately, to obtain the funding for an active soil depressurization or active system, or do an HVAC replacement due to contracting restraints. There may also be some buildings where conventional mitigation strategies such as ASD are just not practical. For example, sensitive compartment information facilities, or SCIFs, are these very top secure vaults that you're not doing any drilling or construction in there. In these cases, RDP measurements can be used to determine the actual EF and exposure. And simple RDP mitigation strategies such as increasing air circulation with fans supplemented with filters can increase the played out and reduce the exposure and health risk. So I just want to review some measurement terms real quick, because I'm going to be talking about working levels and picocuries per liter of air. So radon decay products, or RDPs, are measured in working levels. These come from historical and health risk studies. They're derived from the actual levels that uranium miners were working in, and the guidance is 0.02. And this is also the only exposure that's codified into law for workers. Radon is measured in picocuries per liter of air, as we all know, in the US. And these are consumer measurements. Radon is measured using more simple devices compared to RDPs that provide a surrogate measure of RDPs and exposure. RDP devices do have to also measure airflow, so they're a little bit more refined and costly compared to the radon. The radon action level is 4 picocuries per liter of air, and that is derived from that 0.02 working level and also an assumed equilibrium factor of 50%. So you can see on the equation on the right where you get that 4 picocuries per liter action level from. It's the 0.02 working levels times 100 divided by the assumed equilibrium factor of 50%. So the radon measurements are only accurate if the assumed EF is the actual EF, but there are things that can impact the equilibrium factor, which I'll review in a couple slides. And just a quick review of radon decay products, or RDPs. So RDPs come from the radioactive breakdown of gas. A portion of the RDPs are going to play out because they are positively charged. They will stick to everything. And some are going to stick to a bunch of surfaces, but there will be another portion that stay suspended in the air, stuck to the particles in the air. And on the right, there's the radon breakdown chain, which is probably very familiar to a lot of people. So I'm just going to point out the polonium-218 and polonium-214 radon decay products that have extremely short half-lives, and they also produce the alpha particle. So the alpha particles emitted by the RDPs, specifically the polonium-218 and 214, are what provide over 95% of the radiation dose to the lungs. So those are the biggest health risks. RDP played out and health risks. So as I mentioned, those charged RDPs readily attach to surfaces and suspended particles. The RDPs attached to the particles in the air can pass through your nasal passage and into your lung. And when they break down and emit those alpha particles that are pretty large compared to your DNA, they can do some damage. That's where the health risk comes from. However, the RDPs attached to the surfaces are not suspended in the air, and you're not going to breathe those in. So the equilibrium factor expresses the percentage of the RDPs that are suspended in the air compared to those that are plated out. The greater the played out, the lower the equilibrium factor and the lower the exposure. Air circulation, media filters, and dust and smoke in the air can all impact equilibrium factor. And in the little diagram on the left, you can see there's radon entering into the building. The radon breaks down into its radon decay products. There's 4 that are suspended in the air, and there's 4 that are plated out, so you get an equilibrium of 50%. And then I also want to note that the positive or negative pressure is what's determining how much radon is actually entering into the building. So if that building is under positive pressure, it's going to help keep the radon gas out. However, if that building is under negative pressure because of imbalanced HVAC or something, then it's going to really draw that radon gas into the building. All right, so I'm going to review 3 case studies from the testing we did the last couple of years at military installations. We did testing across the continental US, including Alaska. We did year-long, long-term radon measurement using EPIRMs, and we followed the Navy Radon Assessment and Mitigation Program, or NAVRAM protocols. Those use the EPA guidance. And the buildings that we tested range from large commercial or administrative buildings to barracks and unaccompanied housing, hangars, those SCIF secure facilities, laboratories, and other unique places. The mitigation approaches we used were specific to each building, and they were based on the design, the function of the building, the security of the building, and then the post-testing investigation and diagnostics. The table shows a summary of all the testing. So we tested across 13 installations. There were 320 buildings tested, including over 3,300 individual rooms or locations. Of the 320 buildings that we tested, 15 had elevated radon, and that included 100 individual rooms within those buildings. Some buildings had, only a couple rooms that were elevated, and others had a lot of rooms elevated, depending on where the building was located, and was very building specific. We performed RDP measurements at 4 of the 15 buildings that were elevated. I wanted to note that the exposure at all 4 of those buildings was below the 0.02 working levels, and we saw equilibrium factors all below 30% and some even below 15%. HVAC balance center repair was performed at 10 of the 15 buildings with elevated radon, and active mitigation systems were installed at 2 of the 15 buildings that had elevated radon. So the first case study example I wanted to discuss was a unit ventilator repair conducted at barracks on a military installation. So there were several barracks on this installation, and they all came back with elevated radon, which is very unique because no other building on that installation had elevated radon, so we were very curious as to what was going on. None of these buildings had central AC. They all had these unit ventilators. And so we thought, okay, this might be the culprit. We wanted to do an investigation. So these pictures show the external view of the ventilators. You can see them under the window. Then you have an interior view of the ventilators, and on the right, there's a picture of the ventilator with the cover off. And in the zoomed in picture, you can see that there's this mechanical vent control where you could open a vent to open or close to allow fresh air, and it was stuck on close. So we pulled all of the units, and you can see that there were shipping screws that were never removed from when these units were placed into the building. So that vent was never opening. They were never getting any fresh air into the rooms, these poor people living in the barracks. And then, so the shipping screws were removed, and then you could make sure that the mechanical vent control could open and close. And here's one more picture of the close-up of the interior of the ventilator behind the mesh. So it took about 2 people at each unit, 30 minutes. They pulled all the units, they removed those shipping screws that were still there, they cleaned out the interior, they made sure that vent was working properly, set it to open. adjusted the preventative maintenance to make sure it was kept open so that there was fresh air, and then we followed up with radon measurements to test whether repairing that would reduce radon levels. And here's just a floor plan that shows the barracks. You can see there's a lot of rooms. The text in red is the elevated room, so you can see a large portion of this barracks had elevated radon. And the light, the color's not coming up very good, but anyway, there was sequential short-term testing conducted afterwards, and it was very low. This graph demonstrates very clearly the decrease in radon before and after the repairs were made. So we have the room numbers on the x-axis and radon and picocuries per liter. On the y-axis, the blue columns show the radon right after the long-term assessment, and the red columns show the radon after the repairs were made, and there was a significant decrease in radon. So case study 2 is an active system that was installed in one of the buildings. This is a large, secure facility at one of the installations. Again, the red text showed the elevated radon. There's a clear difference in radon levels between one end of the building and the other. There were actually 2 HVAC units in this building, and the right side of the building had an upgraded system that had supplied air makeup. The elevated side also had a basement, and within that basement there were 2 open groundwater sumps. We did grab sampling in the sumps, and they had very high radon concentrations, over 150 picocuries per liter, so it was very obvious that was the source of the radon in the building. So our subject matter expert helped our client design a active system that was installed by the military, and it included modifying new sump lids, so retrofitting those and sealing them. And there would be 2 4-inch Schedule 40 PVC DWE pipe from the sumps to a common pipe that had a radon fan above the roof and would exhaust the radon outside of the roof. The fan had the variable speed. For the initial test, it was set to max, and then there was a performance indicator on the system, a U2 manometer with a range of 0 to 5 inches of water column. And there's a very rough schematic because they could not take any pictures in this building, but you can see in the basement there's just 2 sumps and the PVC coming from them connecting to one central pipe and exhausting the radon out. And here is a graph that shows the decrease in radon before and after that system activation. So you have the room numbers along the x-axis, again in the radon and picocuries per liter along the y-axis, and you can see a decrease in radon in all of the rooms, especially the basement where it was over 10 picocuries per liter and it was reduced to about 2. And the third case study I want to talk about today is RDP measurements that were applied in a difficult to mitigate SCIF, so that secure facility within a basement and sub-basement of a military facility. The space had a lot of surface area and a lot of air circulation that helped facilitate RDP plate out. It had a lot of computers and servers in there, so air movement to keep everything cool and clean. We used direct measurements of radon and RDPs to calculate the actual exposure and risk. We continuously measured radon and RDPs for 2 days under normal conditions to get a baseline, and then we added fans and filters to see its effect on RDPs for what was supposed to be 4 days, but there was a storm that created a power outage, and so we only got a couple days with the fans and filters. But you can see in the diagram that top level is actually the basement, and then there's stairs leading down to a sub-basement, so there's a ceiling AC that's circulating air in there, as well as a closet with forced air into a mechanical room with even more servers. And down in the sub-basement, there's another AC unit circulating air, as well as a unit ventilator that appeared to be drawing air from the subgrade. And we have the smiley faces show where we put the air filters, and the lightning bolts show where we put the fans. So we put a set up in the basement and then one in the sub-basement as well. And this graph shows the continuous radon in blue over the study period and the continuous RDPs over the study period in the red line. And you can see the first couple days under normal conditions, the RDPs are low and below the level due to all that air circulation and movement. Then when we put the air cleaners and fans on, those RDPs dipped to almost undetectable levels. Then there was a storm that came in, there was a power outage. The radon device did have a backup battery, so we could continue to measure radon, but the air cleaners and the fans turned off. When the power came back on, the RDPs did come back online, so you can see that the radon actually dipped when the power was out, indicating that that space is normally under negative pressure and it's drawing radon gas in. When the power was out, it went neutral, the radon dipped, the RDPs would dip too. If there's no radon, there's gonna be no RDPs. And then when the power came back on, you can see that spike when that room is going under negative pressure again. But what you see is the RDPs still remain very low because there's so much air circulation in that space. It's plating out all of the RDPs. So our recommendation was, keep the fans and cleaners on because they are reducing the RDPs, even though under normal conditions the RDPs are still really low. And here's just a picture of the equipment we used for the RDP study. So the Thomson-Nielsen and BladeWorks EP-Cam did the continuous RDP measurements. We used the RADON CRM continuous radon monitor for the radon measurements, and then we also had a RADON RIPSU integrating RDP and radon device that is not continuous, but we had it to support, to verify the other results. And I just have one conclusion slide. So conclusions from these studies: RDP measurements provide the actual exposure information due to typical low equilibrium factors and non-residential buildings such as these. Exposure is often under the action level and can reduce occupant concerns in the interim before a mitigation system is installed, or can be used as an alternative mitigation approach in difficult to mitigate buildings or spaces like that of the SCIF or secure facilities. HVAC investigation and balancing repair is a cost-effective and quick way to determine if the air ventilation system is the culprit. And no matter what the mitigation strategy used, whether it's putting in an active system, balancing the HVAC, or doing a repair, or mitigating RDPs, remember that that building needs to be retested at least every 2 years. And especially if it is the HVAC that's imbalanced, then it's not just the elevated rooms, it's that whole structure needs to be retested, because rooms that were previously not elevated could become elevated if that HVAC ends up not working properly again in the future. And then also remember that every building space is unique and requires diagnostics and investigation to provide the best and most cost-effective mitigation approach. So that is it. I might have some time for questions. I do want to do a special acknowledgement to Martin Shea, who did a lot of the RDP and follow-up testing, and then also Doug Clatter, because his guidance and expertise were invaluable for these projects.
Very good. Thank you,
Okay.
Rachel. If someone has a question, yeah, please go ahead. And if someone has a question, please come forward to the mic so that our remote people can also hear your question. It would be helpful. There is no mic in the room, so if you just please come up, Mike.
Well, my main question is...
Can you? Okay, I'll repeat it then.
No, I'll talk about it.
Well, I'm just saying, for the people who are remote, I'm just trying to help them.
So my main question is use RDP detectors. How do you do annual calibrations, or where do you do them? Because I don't think there's any place in the U.S. you can do that.
Okay, so Marty, do you have a question for the RDP measurement devices? I think we sent them to Canada, but I will let him.
And do you know the company that?
Yeah, I'm Marty. I helped do the RDP portions of the test. Yeah, so for the US specifically, there is not a lab that specifically does RDP calibration, but Canada actually does. They actually do a little more, certainly more than the US, more RDP related work. So yeah, Canada is wants to do that.
Did you calibrate the instruments in Canada prior to doing these measurements?
The question was, did you calibrate the instruments in Canada prior to doing the measurements?
Me personally, I did not personally, but yes. So yes, the answer to your question is yes. The instruments were calibrated prior to the RDP studies being done.
Oh, they were. I don't know if those instruments are available. The Thomson-Nielsen's out of business, so that instrument's no longer available. And I don't know if the e-RIPS is still being marketed. Is that being marketed? Can you purchase any of these instruments?
You can still purchase the RIPS through RADON website. It's still on there, but it's not a continuous monitor.
And how Canadian unit, can you purchase that unit? There was some Canadian, 235 instrument you had too, I didn't.
We had the BladeWorks EP Cam.
Yeah. It's not available?
Oh, no, so,
It is available, okay.
it is, yeah, that's not a
I'm
Canadian.
familiar with it, I just didn't know.
So that one was actually recommended to